In this presentation, I am going to explain square wave generation using operational amplifier. Let us see square wave generator, that's also called Astable multivibrator, using op-amp. This is a very widely using square wave generator. It's a very simple also. In this one, this is a very simple op-amp square wave generator and also called free running oscillator. That is, it is automatically will be getting a square wave output if you connect like this one, and that is why it is called a free running oscillator. Therefore, here the principle of generation of the square wave output is to force the operation amplifier to operate in the saturation region. For op-amp will be operating in the saturation region so that the output voltage will be either plus Vsat or minus Vsat. It is operating in the saturation region. Now in this one, this is the inverting input, this is the non-inverting input, and the output, that is output will be, as I told you, either it is plus Vsat or minus Vsat. For example, if it is a plus Vsat, that voltage is divided by two resistors R1 and R2, and this voltage is given by whatever this voltage, that is V0, if you take it as V0, V0 divided by R2, H0 divided by R1 plus R2 into R2. If V0 equal to plus Vsat, Vsat divided by R1 plus R2 into R2. That is the called beta V0. If V0 is this voltage, it is equal to beta V0 is the feedback voltage, and that is given as a positive input to the op-amp. And here the negative input, between the output and the negative input, you are connecting a resistor as a feedback path, and there is a capacitor that is connected at the inverting terminal, and that is grounded at this end, so that there is a charging of the capacitor. That is, as for example, if it is a plus Vsat, this will be charged, capacitor will be charging through this path, and once this voltage is reaching to this voltage, that is beta times plus Vsat, then output will be changing. Therefore, this is a we can see the working in the next slides. Anyway, this is output will be either plus Vsat and minus Vsat, and this is the feedback path, and output is also fed back. That is, this output is fed back through a feedback network like two resistors R1 and R2, it's a potential divider, and this voltage is given by Vsat divided by R1 plus R2 into R2, and by means of the the feedback is given, the output is fed back. Another thing, this is one method of the positive feedback, and here also output is also fed back to the inverting terminal through a RC combination, that is a negative terminal, after integrating by means of a low pass RC network. For this is, we can say, a low pass RC network. It is just like an integrator. It is getting charged, the capacitor is getting charged. Now the feedback factor, let us see what is the feedback factor. That is, output voltage is fed back to the non-inverting terminal like this one, and the feedback factor beta, that is given by the ratio R2 divided by R1 plus R2. Therefore, this voltage is equal to V0 divided by R1 plus R2 into R2, or beta times V0. That is the voltage that is coming to the non-inverting terminal. Therefore, the beta is defined as feedback factor is equal to R2 divided by R1 plus R2, and the feedback voltage, the voltage that is fed back to the non-inverting terminal, that's called beta times V0, which is equal to R2 divided by R1 plus R2 into whatever this output voltage V0. That's called beta times V0. That is the voltage that is fed back. This one is the beta V0 that is fed back to the non-inverting input. And here the reference voltage, as I told you, the output voltage can be either plus Vsat or minus Vsat, because this is working in a saturation region. Now, if this is plus Vsat, the feedback voltage will become beta times Vsat plus beta times Vsat, and if this is voltage equal to minus Vsat, this feedback voltage will become minus beta Vsat. Therefore, the reference voltage is equal to beta times V0, and V0 can be either plus Vsat or minus Vsat. So the reference voltage, that is the voltage that is coming, this is the reference voltage that is marked as, that's a feedback, positive feedback voltage. This reference voltage can be either plus beta Vsat if this is a plus Vsat, or it can be minus beta Vsat if this is equal to minus Vsat. Anyway, this is the voltage, V reference voltage coming to the non-inverting terminal, and to the inverting terminal, from the output it is fed back through a resistor, and this is capacitor is grounded, and this is forming an integrated degradating path. This continuing the square wave generator, or also called a stable multivibrator, the same circuit in which this is the feedback path and this is the output is connected to the inverting terminal through a resistor and a capacitor is the. Now consider an instant of the time when the input is equal to plus V sat. First assume that the output. Consider an instant the time when the output is actually this is when output is equal to plus V sat. Consider an instant of time when the output is plus V sat. That is when this output voltage equal to plus V sat. Now, when this is equal to plus V sat, the capacitor will be charging through this path, through this R and this capacitor. The capacitor gets charged through this, and the capacitor starts charging towards, that is the capacitor will be charging towards plus V sat, and through this resistor R, through this resistor capacitor gets charged towards plus V sat. But at the same time you can see that when this voltage is equal to beta times V naught or beta times V sat. Once the capacitor voltage is just exceeding the beta V sat, beta equal to R2 divided by R1 plus R2, when just exceeding here, you can see that one, previously it was plus V sat. Once this voltage is exceeding beta V sat, here that will be changing to minus V sat. Output will be changing to minus V sat. That is what is happening here. When the capacitor is charging and that is towards V sat, but once the voltage capacitor voltage, once this voltage reaches to beta time V sat, where beta equal to R2 divided by R1 plus R2, at that time, because already the reference voltage equal to beta times V sat, once this voltage is just crossing this voltage, the output will be changing to, that is output will be changing from plus V sat to minus V sat. That is output changes to minus V sat. So the capacitor voltage exceeds the plus V sat. The reference, I mean that's the reference voltage that's coming here. The output is driven, or that is driven to minus V sat. It is to be minus V sat. And here now after once this voltage is equal to minus V sat, which is already the capacitor is charged to plus V sat, and this voltage has changed to minus V sat, this capacitor discharges through this R, that is the capacitor discharges, that is to 0, and again that is charging in the reverse direction towards minus V sat. Towards this capacitor is charging in the reverse direction with the minus here and plus here in the reverse direction towards minus V sat. Because once this voltage has been changed to minus V sat, the feedback voltage or reference voltage is now changed to minus beta V sat. And once this is discharging and charging towards minus beta V sat, or just crossing that minus beta V sat, now we can see that one, this output voltage will be again changing from, or this voltage will be more than this one, this voltage changes to plus V sat. Or once this discharging capacitor voltage just crosses minus beta V sat, output is again changing from minus V sat to plus V sat. It is minus V sat to plus V sat is changing. Then that will be repeating. Again, when it is plus V sat, again that gets capacitor is charged, and this voltage equal to plus beta V sat. Once this voltage is exceeding this plus V sat, this output is changing to minus. Therefore, that is repeating like this one. Therefore, he will be getting a complete square wave output at this point. At V0 will be a square wave output. And this voltage, if you see the voltage at this point, the inverting terminal, that voltage is the capacitor that will be charging from minus beta V sat to plus beta V sat. And from here, my plus beta V sat, so it is discharging towards 0 and charging in the minus beta V sat. Therefore, this is the capacitor charging discharging waveform. That is the voltage at this inverting terminal, and beta reference is the voltage that is coming, reference voltage, that is equal to beta V naught, that is the reference voltage coming, and the output voltage will be either plus V sat or minus V sat. That is, you are getting a square output here. Therefore, now the capacitor starts to discharge through R, and again that gets and then again gets charged towards minus V sat. When the output switches to minus, when the output switches to minus V sat, capacitor C charges more and more negatively until the voltage is exceeding minus beta V sat here. And now once at this point, the capacitor as a capacitor voltage reaches to this point, that is voltage. Now this will be just exceeding. After that, this will be exceeding this, or output voltage will be changing from minus Vsat to plus Vsat. Now output voltage changes from minus Vsat to plus Vsat, and this cycle will be repeating. Therefore, you will be getting a square output at this point, and the beta value that is equal to R2 divided by R1 plus R2, and beta times V0 is the reference voltage. Continuing the square wave generator, we have to calculate what is the frequency of oscillation. We are getting a square wave output at this point. What is the frequency of this oscillation? In order to derive that equation, the frequency is determined by the time it takes the capacitor to change from minus Vsat to plus Vsat, and vice versa. Or of course, if the time period is this much, total time period is this one, and T1 period is the duration for which the capacitor voltage is changing from, that is the voltage at this point is changing from minus beta Vsat to the plus beta Vsat. And again, then if it is exceeding that one, the output is changing from plus Vsat to minus Vsat. Therefore, this duration to the capacitor voltage to change from minus beta Vsat to the plus B Vsat, that is the half of the time period, or that is equal to capital T1. Total time period will become 2 times T1. Therefore, here, if you calculate the equation, or if you derive the equation for the capacitor voltage, charging capacitor voltage here, VCT is given by the only equation is that capacitor voltage at any instant is equal to the final voltage V final plus V initial minus V final into e raised to minus t by RC. This is a general equation for the capacitor voltage. When capacitor is charging through R and C, that is output voltage assumed here equal to plus Vsat. Therefore, the capacitor voltage is charging, and the voltage at this point, that's the capacitor voltage at any instant, is calculated as the final voltage plus initial minus final voltage Vi minus Vf into e raised to minus t by Rc. Now, if you see here, if the capacitor voltage change here, it is a final voltage that is going to charge up to plus Vsat. So the final voltage is equal to plus Vsat, and the initial voltage that is given, that is charging from the initial voltage of minus beta Vsat. Therefore, substituting those values in this equation, the capacitor voltage at any instant of this one, the capacitor voltage at any instant is given by a final voltage is that will be finally charging, that is going, if it is charging, it is finally that goes to plus Vsat. Therefore, plus Vsat or Vsat plus initial minus beta Vsat, initial minus finals minus Vsat into e raised to minus t by Rc. Therefore, this is the equation of the capacitor voltage at this point. This equation, that capacitor voltage at any instant, is calculated by this equation 2. Now, at time t equal to t1, if you see at time t equal to t1 here, a transition is taking place. Output is changing from plus Vsat to minus Vsat, because once this voltage is just crossing this reference voltage, output is changing from plus Vsat to minus Vsat. Therefore, at time t equal to t1, then you can calculate what is the capacitor voltage. Capacitor voltage is equal to plus Vsat. Therefore, plus Vsat, that is, we can say that the capacitor at t equal to Tm, the voltage across the capacitor is become plus beta Vsat, and the output switches from plus Vsat to minus Vsat. The output is exchanging from plus Vsat to minus Vsat. Now, if you substitute in this equation here, that is Vc, that is capacitor voltage at time t equal to capital T1, that is equal to plus beta Vsat, which is equal to, here again, we are substituting this equation, Vsat minus, here Vsat minus Vsat into, here in this equation, we are from this equation we are deriving this one. Here it is equal to 1 plus beta into e raised to minus capital T1 divided by Rc. Because here, this is the equation for the capacitor at any instant during charging, and here you are rearranging this one, and you will be getting, it is equal to Vsat minus Vsat into 1 plus beta into e raised to minus t by Rc. Therefore, we are arranging this equation in this form, equation 2, and in that one, if you substitute that one, you will be getting what is the from this equation you can calculate what is the time period t1. Therefore, here substituting here in this equation, if it is that b sat into 1 plus beta into e raised to t1 by rc equal to v sat into 1 minus beta. For here in this equation v sat into 1 minus beta. Now from this equation you can reduce it is equal to e raised to minus t1 by rc equal to 1 minus beta divided by 1 plus beta, or e raised to t1 by rc equal to 1 plus beta divided by 1 minus beta. Or from this equation you can get what is t1. If you take the logarithm ln natural logarithm here, t1 equal to rc into, that is rc into natural logarithm of 1 plus beta divided by 1 minus beta. Therefore, this is the equation for this time period t1, because half of the time period, total time period will be t, capital T, that is twice t1, and t1 is given by the product of r and c, the time constant r into c into natural logarithm of 1 plus beta divided by 1 minus beta, where beta equal to r2 divided by r1 plus r2. Continuing the square wave generator frequency calculation, here we have a derived equation for the time period t1. T1 means that this duration from this to half of the time period actually. Total time period is equal to 2 times t1. Total time period from 0 to this one, 2 times t1. T1 we have derived, it is equal to rc natural logarithm of 1 plus beta divided by 1 minus beta. R is resistance, R feedback resistance. C is this capacitor which is connected to the inverting terminal. Capacitor is charging through this one, and once this voltage is reaching to that beta V sat, output is changing. And here the corresponding T1 you calculated, which is equal to RC natural logarithm 1 plus beta divided by 1 minus beta. And the total time period, if you calculate the total time period, is equal to twice the T1, which is equal to 2RC natural logarithm of 1 plus beta divided by 1 minus beta. Therefore, the total time period of the square waveform is given by 2RC natural logarithm of 1 plus beta divided by 1 minus beta, where beta is given by R2 divided by R1 plus R2. Once you calculate the total time period T, the output frequency is 1 by time period, 1 by capital T, or this is equal to 1 by 2RC natural logarithm of 1 plus beta divided by 1 minus beta. Therefore, this is the equation for the output frequency of a square wave, a stable operation of a op-amp. And here we can see the output frequency is given by 1 by 2RC natural logarithm of 1 plus beta divided by 1 minus beta, where R is the feedback resistance and C is the capacitance which is connected to the inverting input, and beta is given by R2 divided by R1 plus R2 feedback factor, and here output feedback is beta times V0 is feedback, that is given as the reference. And once this voltage is crossing this reference, it will be changing, output is changing from plus V sat to minus V sat. Again that will be discharging, and once this voltage is just crossing this value, again that is transition taking place from minus beta minus V sat to plus V sat. Therefore, we are getting a square waveform at the output, and the frequency of oscillation of this square wave, that is equal to twice the time period T1, which is equal to 2RC natural logarithm of 1 plus beta divided by 1 minus beta. Therefore, the frequency is given by 1 by T, which is equal to 1 by 2RC natural logarithm of 1 plus beta divided by 1 minus beta. Now, if you substitute that, if R1 equal to R2, that is, if you substitute both are equal, if R1 is equal to R2, beta will become equal to 0.5. In that case, beta will become 0.5, and substituting the value of beta equal to 0.5 here, 1 plus 0.5 divided by 1 minus 0.5, or 1.5 divided by 0.5, or it is natural logarithm of 3. Therefore, output time period is given by 2RC natural logarithm of 3. We will be getting 2RC natural logarithm of 3 is the output time period, and the frequency is equal to 1 by T. Therefore, if R1 equal to R2, if these are equal, it is equal to 2RC natural logarithm of 3. Now, if R1 equal to 1.16 R2, if R1 is equal to 1.16 R2, if you substitute like that one, if you select R1 as such as 1.16 R2, then if you calculate again beta, R2 divided by R1 plus R2, 1.16 R2 plus R2, or it will become, it is 0.463 you will be getting. Beta value you will be getting 0.463. Now substituting this 0.463 in this equation, then you'll be getting 1 plus 0.463 here, 1 plus beta, and here 1 minus 0.463. And then if you calculate the total time period t here, t equal to 2RC natural logarithm of 1 plus 0.463 divided by 1 minus 0.463, or that this, if you take the natural logarithm, this will be equal to unity, and then you'll be getting it is equal to 2RC. Therefore, time period is equal to 2RC if you select R1 equal to 1.16 times R2. Or if you select R1 equal to R2, it is equal to 2RC natural logarithm of 3. Now, in this case, if R1 is selected 1.16 R2, this time period is given by 2RC, or the frequency, output frequency is given by 1 by capital T or 1 by 2RC. Therefore, this is a special case when you select when you select R1 equal to 1.16 R2. Therefore, this is the equation for the output frequency, and this is the time period of a astable operation, astable square wave here. Now continuing the square wave generator operation here, as we have already seen here, a positive feedback with R1 R2, that is beta times V naught is taken, that is given to a positive input, a non-inverting input, and to the inverting input through an RC, that is a integrator circuit, where the capacitor gets charged. And this is already we have seen what is a square wave generator. Now the square wave generator, the output will be either plus VSAT or minus VSAT. But if you want to, if you are connecting a Zener like this one, you can limit the voltage output. For your two Zener diodes are connected with a Zener breakdown voltage, say VZ is the Zener breakdown voltage. This is connected, the back to back it is connected, and then this voltage will be, this output voltage will be plus VZ, and here the output voltage will become the V0 peak. The one side output voltage will become VZ plus VD, other side it will become minus VZ, minus of VZ plus VD. Of the total peak to peak voltage, that is the voltage from this to this one, peak to peak voltage of the square output will become twice VZ plus VD. You can limit the output voltage limit. This voltage can be limited by properly selecting the Zener breakdown voltage. If you select the proper Zener voltage, Zener voltage having this required breakdown voltage, then you can limit the output voltage. This output voltage can be limited. Otherwise, output will be either plus VSAT or minus VSAT. If you want to bring to that voltage the limited voltage at plus side and minus side, you can connect a Zener in this fashion, so that this voltage will become, this voltage will become VZ plus VD, and this will become minus of VZ plus VD. Total voltage peak to peak will become twice VZ plus VD. This is a one modification of a square wave generator to limit the output voltage using a Zener voltage. So Zener diodes, it's called the Zener diodes, because back to back connected Zener diodes. And the asymmetrical square wave generator means, in this case you are getting on period is same as off period. Whatever we have already explained, on period equal to off period. But if you want to change the on period and off period, rather than connecting this this point to ground, rather than connecting to this ground, you can connect a reference voltage. That is, a reference voltage can be connected at this terminal, at this one, and then so that this voltage magnitude can be changed, and that voltage, that is here, capacitor voltage swings between. In that case, if you apply a reference voltage of a capital V or a voltage V here, in previous case the capacitor voltage was changing from minus beta VSAT to plus beta VSAT, then again discharging from plus beta VSAT to minus beta VSAT. But in this case, if you add a reference voltage like this one, the swinging will become plus beta VSAT plus V and minus beta VSAT plus V. Therefore, there will be unsymmetrical swing will be there, so that on period will not be equal to off period. Therefore, whenever you want to have a generate a unsymmetrical square wave, meaning that on period is not equal to off period, if you want to generate that one, you have to add a voltage at this point, so that this on period will not be same as the off period. Therefore, asymmetrical square wave can be generated by connecting a voltage at this point, that rather than grounding this one, you are connecting a voltage V, so that the capacitor voltage will be swinging between beta VSAT plus V and minus beta VSAT plus B, and on period will not be same as the off period. That is what is called asymmetrical square wave generator.